Crash Course Instrumentation Episode 2 Boiler Water Level Control System. Welcome back to Crash Course Instrumentation. In this episode, we're diving into our first real-world control system, a boiler water level control system, a classic and essential example of industrial feedback. So why does boiler level matter? Boilers produce steam for heating, power generation, or process operations. But if the water level gets too low, you risk overheating, tube rupture, and even catastrophic failure. Too high? You may flood the steam lines, carry water into turbines, and reduce overall efficiency. That's why maintaining the right water level is absolutely critical, not just for efficiency, but for safety. A bit of history. Boiler control systems have been around for more than a century. In the early days of the Industrial Revolution, boiler operators had to manually check sight glasses and turn valves based on their own judgment. Mistakes often led to boiler explosions, which were sadly common in the 1800s. It wasn't until the early 20th century that automatic float switches and mechanical regulators began to take over. The introduction of pneumatic controllers, like those made by companies such as Foxborough and Honeywell, revolutionized control precision in the mid-1900s. Today, we rely on smart sensors and digital control systems to manage everything in real time. This is where instrumentation steps in. Let's break down the components of a typical boiler level control loop. 1. Level sensor, or transmitter. Measures the actual water level in the boiler drum and converts it into a standard electrical or pneumatic signal. This becomes the process variable, or PV. Common level transmitters include differential pressure sensors, guided wave radar, and capacitance probes. 2. Controller. Compares the measured level, PV, to a set point, SP, the desired water level. It calculates an error and adjusts its output accordingly. This output is called the controller output, or CO. The controller might be a standalone PID controller, part of a PLC, or integrated into a DCS. 3. Control valve, final control element. Receives the controller output and adjusts the flow of feed water into the boiler to bring the level back to the set point. It may be actuated pneumatically, electrically, or hydraulically. This is called a feedback loop, because the system is constantly checking itself and making corrections in real time. Most boiler control systems today use a PID controller, which stands for proportional, reacts to the size of the error. Integral, reacts to how long the error has existed. Derivative, reacts to how quickly the error is changing. Together, these actions create a control response that's fast, smooth, and accurate. Let's put it into context. Imagine a sudden demand for steam. The water level starts dropping. The level sensor notices the change, the controller calculates the error, and the control valve opens up to let in more water. All of this happens automatically, without a human having to manually open or close valves. In many modern systems, this signal chain is digital. The level transmitter might use a 420 milliamp signal to represent the measured level. And the controller could be part of a programmable logic controller, PLC, or a distributed control system, DCS. And the valve could be equipped with a smart positioner, capable of receiving digital commands via HART, Foundation Field Bus, or similar protocols. You might also find safety interlocks programmed in. If the level drops too low, a shutdown sequence might trigger. These are often backed up by hardwired alarms and switches for redundancy. Boiler-level systems are a fantastic example of how instrumentation creates safe, self-correcting, and efficient processes. It's not magic. It's measurement, logic, and automation working together. And when you understand the system, you can maintain it, troubleshoot it, and improve it. This case comes from Lessons in Industrial Instrumentation by Tony Couphalt. Be sure to check out the full text at the link below. Like and subscribe to stay on top of this series as we explore more real-world systems in action. Watch all episodes. www.youtube.com/Crash Course Instrumentation. Join the discussion. www.facebook.com. Groups 132542904737541.